This section we're going to be talking about PV diagrams, which are really just an application of the ideal gas law that we covered in the previous section. So we're just graphing it, and we're talking about different processes that can transition from one state to another. So let's get started.
So let's talk PV diagrams, okay? So let's say we pick a little point here. What can you, now that we know that we have PV equals nRT, let's say we have a sealed container. Okay, so what's, yes, kilopascals. So what's the volume of this thing? 3 meters cubed. What's the pressure? 10 kilopascals. So 10 times 10 to the third pascals. So about 10 times, less than atmospheric pressure. Right? That's the one. Yeah. Okay, what else can you figure out about it? Let's say we know there's 1 mole of this gas. Yeah, you can figure out the temperature. Okay, so how would you figure out the temperature? Yeah, you plug that shit in to be to be specific. Okay, so this point represents a particular state of the gas, and we know it's a state because we can figure out all the state variables. We have P, V, and T. Okay, just looking at this graph, you can figure out the state variables as long as you're given the number of moles. All right. Then over here, let's say we have the same number of moles. We have a new state. Okay, and over here we have another state. And if we want to go back and forth between the states, that means moles and R are constant, and so that means these things are all related by this. Okay, which is just saying, you know, these are all going to be equal to NR because it's 1 times 8.31. So all of, when you multiply PV divided by T for all of these, they should just give you 8.31. Okay, so they're all equal. So when you're going back and forth between these states, all right, on a PV diagram, you can figure a lot out just looking at the graph. Okay, and so we can figure out the temperatures. This one's 3,600, this one's about 900, this one's about 600, so this one's really hot. And you can see the temperature as you move this way gets hotter. As you move this way, it gets colder. Okay, and we'll see what that actually looks like in a minute. But the other thing about a PV diagram, these give you the states, but when you use a PV diagram directly, it should tell you how you get from state to state. Okay, and I'll show you what that means. Okay, for this, if we're in state 1 and we want to get to state 2, any lines that connect those 2 points are considered possible. Okay, but here's 2 different ways you can get there. All right, in this case, you have an isobaric, right, constant volume, right? You change just the pressure, and then you change just the volume. Okay, so you're passing through some temperatures, but these temperatures are all going to be less than 900 Kelvin because you're going this way. If you go this way, you've done some other shit, and you go through this crazy temperature. Okay, in either case, you go from this state to this state. All right, you start and end at the same place, but the way you get there is going to vary dramatically. Okay, there's lots of different ways to get from one state to another, and it matters how you do it. Okay? All right. So let's talk about the ways, the standard ways. So any line is possible, but there's some standard ones that are easy to understand and come up a lot. Okay? So we'll start with an isochoric process. What does isochoric mean? Yeah, it's constant volume. It's the least easy to remember because nobody knows what choric means. It's probably Greek or Latin. It's probably Greek. Everything's Greek. It's all Greek to me. So let's say we start with a fixed volume, okay? So how do we usually get a fixed volume in the real world? A sealed container, right? A container that doesn't change shape. So like a balloon, not a great way to get fixed volume, okay? But actually, what does a balloon keep? Pressure, right? What's the pressure inside a balloon when you blow it up? Yeah, 1 atm, right? You have to keep the pressure on either side of the balloon has to be equal, or the balloon changes shape. Okay? So when you have a balloon blown up, you can assume the pressure inside the balloon is 1 atmosphere because the pressure outside the balloon is 1 atmosphere. Okay? And if you change the pressure of the air in the balloon by cooling down the molecules, then you still keep a balance of the 1 ATM, right? It changes the volume and you get back to 1 atmosphere. All right? So the pressure inside and outside of a balloon has to be the same. If you put a balloon underwater, what's going to happen to it? It's going to pop. Why? If it's sealed. What happens to the pressure as you go underwater? It increases. Okay? Yeah. So you have to actually, so this is why airplanes and submarines and things are pressurized, right? If you go up in an airplane, what happens to the pressure of the air? It's lower, right? Yeah, so you have stress, you have forces acting on the outside of your plane because things are trying to push out, okay? So you have to have strong materials or you have to equalize the pressure. You don't want the pressure inside your airplane to be the same as the pressure outside because why? Yeah, you don't want to die. So, because well, it's cold. That's not the bigger issue. You can heat it up. But you need a certain amount of density of oxygen in the air so you don't die. And if you get to the pressure that's outside a plane, that's not enough oxygen for your whole brain thing to work. So that's why when you summit like Everest, you have to take your own oxygen with you in a can because at the top, it's not atmospheric pressure anymore, right? It's thinner air, less pressure, so less oxygen, more dying. Okay. What? Yes. Yeah. Colorado has less drag, right? All right. Okay. So anyway, constant volume. You have a fixed container. All right. So here, let's say this is our volume here. We have some pressure at pressure 1. Now let's add some fire to the same. These were the same to begin with. Now we've increased the pressure. Okay. How do we increase the pressure? Well, we raised the temperature, kept the volume fixed. That means the pressure has to go up because we can't change the number of moles. It's trapped in a container. R is a constant. The only thing that can change is the pressure. Okay. So here is our pressure 2. But what do we notice about the volume? It's constant, right? If it's along a vertical line, we have not changed the volume. And so how would you describe this process? Isochoric. You go from pressure 1 to pressure 2. Okay? And if you took this and cooled it back down to here, you just go back down. But the arrow is important. It tells you where you started and where you end.
Isochoric describes the constant volume. So how do you describe that?
Yeah, just isochoric process.
Even if going in reverse?
Yeah, isochoric. This would be an increase in pressure or a decrease in pressure would also be isochoric as long as it stays along a vertical line. Yes. Okay. Here's a question. We think it will increase. Let's discuss. Now remember, it's over a long period of time, okay? Better. D. That's actually a decent answer. So nothing's going to happen over time. Because what's going to happen instantaneously, right, is you heat up the gas, and we know that's going to increase the pressure of the gas, okay? Well, if the pressure inside is bigger than the pressure outside and the piston's free to move, what does the piston do? It goes up, okay? When does it stop going up? When the pressure is equal again, okay? And so that means this gas, as if you do this slow enough, is always going to be at what pressure? 1 atmosphere, okay? It's going to maintain 1 atmosphere. Now, it'll fluctuate a little, right? It'll go up and then it'll move, and it'll go up and it'll move, but it'll happen pretty fast. So this way, as long as you don't heat this thing up too fast, this is a way to always keep the pressure the same, all right? The pressure inside has to equal the pressure outside because you're just balancing forces, okay? Anytime there's more pressure inside, it just moves the piston until the pressure's the same, okay? And so we call this an isobaric process, okay? Isobaric process means constant pressure, okay? And just to break down the forces, since we love force diagrams, if you look at the piston from the side, it has weight, okay, mg going down, and then it has another force going down from the air sitting on top of it, okay? So remember, pressure is force over area. So if you want force, you take pressure times area. Okay, so force over area times area, you get force back. Okay, so this is going to be atmospheric pressure times the area, the cross-sectional area of the piston. Okay, going up, you have the pressure of the gas times the same area. All right, that means if you have a movable piston, you can just write this as a force equation, right? We know that P times A minus mg, that's a force equation, right? If you add up the forces, you have this minus this minus this. Okay, we divide through by A, you get something that looks like this. All right, and what this means is as the temperature of the gas increases, the piston's going to move so that this becomes equal again. All right, so a movable piston ensures constant what? Pressure, okay? So as the temperature increases, the volume of the gas increases in order to keep the pressure constant. All right? Wait, what? Capital A is the cross-sectional area of the piston. Okay, so it's not quite that the gas. So if you have a massless piston, then these two things are equal. Okay, if you have a piston with mass, then your pressure is going to depend more on the mass of the piston plus the pressure from the outside. Okay. Gravity. Yeah. Acceleration due to gravity. Yeah, this is the mass of the piston. I know, it's like sometimes we use it for molar mass. This is the mass of the piston, okay? This is G. This is the cross-sectional area of the piston. All right? But as long as you have the same mass, you should have the same pressure. Okay. So let's look at what this looks like. So we have constant pressure, okay? Here's our first situation. That guy has volume 1. Okay, volume 1, that's the pressure. The pressure depends on the mass of the piston and the atmospheric pressure. Okay? Then we add some temperature, right? What do we know about the pressure? Constant, right? Because we have the same piston, but the volume changed. So this is an isobaric process, and this would be called an isobaric expansion. How do we know it's an expansion? The volume got bigger, okay? So if you go this way, it's an expansion. If we went this way, what would it be called? Compression, right? So isobaric compression, all right? So as long as we have a movable piston, we get constant pressure, okay? Movable piston means constant pressure, all right? Yes. Constant explosion.
Okay, so once again, this is a problem, which means please try doing this on your own on some scratch paper before you follow along with the solution. And this would be a good time to pause because I'm about to get started explaining this problem. So pause here, try the problem yourself, and then watch the solution. Okay, so we have this gas. It's occupying some sort of 50 centimeter cubed volume, right? At 50 degrees Celsius, and we want that in Kelvin, and we also want our centimeters to be in meters, although that's less important, and I'll show you why in a minute. It's cooled at constant pressure, right? So constant pressure, that's going to tell us something about our problem, which is that we are dealing with an isobaric system, right? Isobaric means constant pressure. And we want to know the final volume. So let's write down what we know. And then before we even get started, we want to make a prediction about what kind of answer we're going to get. So we know we have our temperature 1, and that's going to be 50 degrees Celsius, which we add 273 to get 323 Kelvin. We know that volume 1 is equal to 50 centimeters cubed. Now, normally we would convert this to meters, but I'll show you why we don't need to do that in a minute. And then temperature 2 is going to be cooler. That's going to be 10 degrees Celsius, which is going to be 283 Kelvin. Remember, we just add 273 to Celsius to get Kelvin. What we don't know is V2. Oops. Okay, so here are our clues. We wrote down our knowns and unknowns. So here's the one thing we don't know. So we're looking for a volume. We'll be able to plot this on a PV diagram, right? So pressure, volume, because it's an isobaric system. That means we're going to have a constant line. So if these are our 2 points, we're going to have some sort of connecting line here. All right, actually, let me draw that better. But we don't necessarily know which way it's going to go. So we know the pressure stays the same, but we know the volume. So one of these is V1, one of these is V2, and the temperature change. So when we look at PV equals nRT, the thing that's not changing here is this. So now we can rewrite this equation so that we can see where all the constants are on one side. So we end up with V over T is equal to NR over P. This whole thing is a constant. So when we have V1 and T1, that's the same as V2 and T2 is equal to the same constant, NR over P, because all of these things stay the same, right? So that means this and this are equal, and we can write V1 over T1 is equal to V2 over T2. Okay, so this is the equation we're going to start with, and this is only useful for isobaric processes, meaning constant pressure. Now, looking at our PV diagram, we want to know, is our volume getting bigger or smaller? Well, let's look at the temperatures, okay? And we can see from our temperatures that we're going from a hotter temperature to a colder temperature. So knowing what we know about an ideal gas, we're going from something hotter to something colder. What do we expect to happen to the volume? Well, we probably expect the volume to get smaller. So we would say this is V1 and this is V2, okay? So we're expecting our system, to move in this direction, okay? So from V1 to V2, so going to a smaller volume. So we expect that V2 is going to be less than V1. So this is our prediction, and hope that means when we get our answer, our volume should be less than 50 centimeters cubed. And if it's not, then we want to worry that we did the problem wrong. Okay, so here's our equation over here, and we're going to start there. We're solving for volume 2. Okay, so when we solve for volume 2, let's bring this up here. We do some algebra and we see that V2 is going to be equal to V1, and then we get T2 over T1. So we can plug in our values, and you can see it's very important that you convert the temperature because this is a ratio. And if you add, since they're not proportional, since Kelvin and Celsius are not proportional, you're just adding a constant. If you don't change it, you'll get the wrong answer. So it's very important because they don't scale. It's not a one-to-one correspondence on the temperature conversion. It's not a multiple. It doesn't cancel. So you have to convert the temperature. However, for the volume, since this is a ratio, and you'll see that Kelvin cancels over here, we don't actually have to convert the volume because if we start with centimeters cubed, we'll get centimeters cubed. Okay, so meters cubed and centimeters cubed, they convert by a multiplier, right? You have 100 centimeters in a meter, and then you just cube that, so you end up with 10 to the 6th centimeters cubed per meter cubed, blah, blah, blah. You don't have to do this conversion because the units of Kelvin cancel, and you just go centimeters cubed to centimeters cubed. Okay, small aside on that. So we get 50 centimeters cubed, and then our temperature 2 is 283 over 323, both Kelvin. And those kelvins should cancel, right? And then when we plug all this in, we end up with a value, and you can see this ratio should give us a smaller value, which is what we want, of 43.8 centimeters cubed. So this is our volume 2, and the good news about that is it does end up being a smaller volume. So volume 2, this one, is equal to 43.8 centimeters cubed, okay? So we started with our prediction, which is that our volume should be getting smaller. That's what we get from our answer. So that's a pretty good check that we did the thing right.
We're back. All right, let's discuss and we'll vote again.
Are they the same gas?
Doesn't matter. Lost somebody. Oh, okay. So, how do we determine pressure? Remember, if we do the force diagram, pressure should be the atmospheric pressure plus the mass of the piston. Does it have anything to do with the gas? No. Okay? So as long as the mass of the piston is the same, and they're in the same room, what do we know about the pressure? It's the same, right? The volume might be different, okay? You can see the volume's different. The number of moles might be different, but pressure is determined by the atmospheric pressure and the mass of the piston. If those are the same, then the pressure is the same. None of the other stuff matters. They don't even have to be at the same temperature. That was just misleading, okay? The only thing that matters for the pressure is that the outside pressure is the same and the piston has the same mass. Okay?
I have a question. If they were the same exact gas, how could they have different volumes?
They could have more moles. Have more of the same gas. Yeah. Okay. Okay. Another question. Better, except for two of you. So, what does the pressure depend on for the gas? The mass of the piston and the atmospheric pressure, which are still the same. It doesn't matter what you do to the gas once it reaches equilibrium, right? The pressure only depends on the outside pressure and the mass of the piston. Okay? So that's going to be pressures are equal. Yes.
If these containers closed,
Uh-huh.
sealed, this would be
Isometric isn't a word that we've learned today.
isochoric. Sorry.
Yeah, if the piston can't move, then it's isochoric. But if the piston can move, then obviously you can change volume, and it's isobaric. So a non-moving piston, a fixed container, is isochoric. Something with a moving piston obviously can change volume. Yeah, so that's isobaric. That's whatever. All right, basically, the result of this is that you always have your pressure of your gas dependent on the mass of the piston and the outside pressure. Okay? Once you reach equilibrium, it only depends on how much your piston weighs and how much atmospheric pressure there is. Yes?
Would it be different if it was in like water?
As long as they're both in water,
Okay.
doesn't matter. Yeah. Yeah, they have to be at the same depth. But yeah, as long as the outside pressure is the same, it doesn't matter what's causing the outside pressure. They should be the same. Okay. All right. So let's talk about the guess what isothermal means? Same temperature, constant temperature. Okay. Not constant heat. Heat can move. So isothermal means constant temperature. So let's say, so why are these things in this lovely water bath? So what happens if you throw something in the ocean? What temperature does it reach? Whatever temperature the ocean is, okay? If you wait long enough, you get thermal equilibrium. So if you have a large body of water, like a water bath, that can regulate your temperature, okay? Even humans, if you stay in the ocean long enough, will reach the same temperature. You'll be dead, but you'll reach the same temperature of the ocean, okay? Your body will burn calories to stay at the temperature you want to be at until it runs out of energy, and then you die. Okay, so we start with this temperature, and then what we do is we slowly press down on the piston, right? So you have to apply an external force. So you're decreasing the volume, okay? So you're changing both the pressure and the volume, and you can see you're changing both pressure and volume until you get over here. Now, this line, what do you know about this line? What's the same on this line? Temperature, okay? So isothermal processes aren't straight lines, they're these curves, all right? And everything along this curve has the same temperature. It's the temperature of this water bath. Now, how do you maintain the same temperature? Well, you have to do this process very slowly. So basically, you change the pressure and volume, but you wait for it to go to the same temperature, and then you do another step. So it's a very slow process. Okay, so isothermal processes must happen slowly. Okay, so yeah, and it turns out, so that's an isothermal compression. You can also have an isothermal expansion, okay, which is going the other way, and that means it's going from a smaller volume to a bigger volume. Okay. Expansion just means smaller volume to bigger volume. Compression means bigger volume to smaller volume. So if you're going this way, that's an expansion. If you're going this way, that's a compression. So it just depends on the arrow. Okay? Now isotherms look like this. They're these curves, and they look like an inverse. Guess why? Because they are an inverse. Because if you think about PV equals nRT, right? If you're looking at the T diagram, the T part of the diagram, okay, that's going to be an inverse. So P, if you keep, sorry, I said that badly. If you keep T constant, that means you have PV equals nRT. This whole thing is a constant. Okay, so your graph looks like P constant 1 over V. That is an inverse curve. Okay, this is your Y, this is your X. This is like saying Y is equal to some constant 1 over X, right? So you're going to get an inverse. If you increase your temperature, okay, then your isotherm moves that way. If you decrease the temperature, it goes the other way, okay? So it goes hotter this way, cooler this way, all right? So temperature increases as you move away from zero, okay? Cooler is closer to your axes, hotter is farther away from your axes. All right. Here's this is for an ideal gas. Just for some comparison, this is for a non-ideal gas, right? Because remember, it doesn't stay a gas. So here's where it's a liquid, here's where it's liquid and vapor, here's where it's gas, okay? And this is what your curves look like. They're all messed up. Yes, they depend on the state, right? And you can see when things are liquids, it behaves differently. But you can see, here's the ideal gas part, right? Because remember, we said ideal gases have to be far away from the condensation point, which is somewhere over here. Okay, if you get close to the condensation point, you get all these little kinks in your curve. If you're far enough away from it, you get these lovely isothermal curves. Okay, so just some food for thought. All right. Okay. Here's a question. tried. We're doing better. The same 8 people are convinced, I think. So I'm just going to say this is B, okay? Because remember, what determines the pressure? Outside pressure and the mass of the piston. So if you want the same pressure, you need the same piston, okay? All right.
So once again, we're dealing with a problem. So you want to try this problem on your own before you watch me do the solution. And even if you follow along with the solution, make sure you can set up the problem without listening or watching me do it. Okay, so right now, pause, attempt to do this on scratch paper, at least set it up so you know what the steps would be, and then you can watch the solution. If you get stuck, watch the solution, but make sure you can do the problem without watching the solution at some point, okay? Definitely before any exams or assessments. So, pause now. I'm about to start explaining this problem. All right, remembering back to example 1, we talked about 1 mole of gas at STP. And so this is a key thing. We're not going to redo this. We know that 1 mole of gas at STP has a particular volume, okay? So that would be 0.224 meters cubed, and we'll come back to that. Now we have these numbered processes. So from step 1 to step 2, we're undergoing an isochoric increase, which means the volume stays the same, but the pressure is increasing, and we're doubling the pressure, okay? It then undergoes an isothermal expansion, meaning the volume is getting bigger and the volume is doubled, okay? But the temperature there stays the same. And then, last but not least, we get an isobaric compression, which means the pressure stays the same, and we return to our initial volume. Okay, so we have 3 transitions here. We have an isochoric, an isothermal, and an isobaric. And we're going to draw the PV diagram, and then we're going to go back and look at the actual numbers, okay? So to draw the PV diagram, I'll start by just drawing P and V, right? So this is pressure, and this is volume. Remember, pressure, the pressure is going to be in pascals, and the volume is going to be in meters cubed. All right, so we're going to start at a point, let's call this 1. So this point right here is at volume 1 and pressure 1, okay? So we'll call this point 1. Now, we start with 1. The very first thing that happens is we have an isochoric increase, okay? So the isochoric increase means that we're going from pressure 1 to pressure 2. And let me see, let me actually move this. Here is our point 1. And then we know that our pressure is doubled. So this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's pressure 2, okay? So since this is an isochoric increase, that means we're going from here to here, and that's the direction that we're moving. So we know pressure 2 should just be twice pressure 1, so we can actually just write this as pressure 2 is equal to 2P1. Okay? Then the next thing that happens, and we're not even using any numbers yet, so we'll do numbers in a minute. The next thing that happens is an isothermal expansion until the volume is doubled, okay? So let's say this is V2. We know this is twice V1, and we know that an isothermal expansion looks like a curve. And we also know that we're returning to our initial volume, and the next thing is going to be isobaric. So even though we don't really know where this dot goes, we know the final process should look like this because it has to be along this line. So it's pretty reasonable to assume that this dot should be here on the same line as the original dot. So this, just going back to the second one, we have an isothermal process. We know the isothermal line looks a little, it's not a good drawing, looks a little curved. So this is an isothermal expansion, and then the volume is doubled, okay? So this would be 0.3, so 0.1, 2, 3. Then we have an isobaric compression, which means we're making the volume smaller. That's what compression means, right? Because expansion means volume gets bigger. Increase means something gets bigger, in this case pressure. Either thermal expansion means volume gets bigger. Compression means volume gets smaller. So the isothermal expansion means we've increased the volume here, then we decrease the volume here, okay? So we return to our initial volume, and now we have our whole drawing for our PV diagram, and this point is also 0.4. Okay, so we start with standard pressure and temperature for 1 mole of gas. We double the pressure without changing the volume, then we double the volume without changing the temperature, and then we half the volume without changing the pressure. So those are our 3 steps. Okay, so we drew our PV diagram for the process, and now we want to actually put in some numbers. So to put in some numbers, we have to start with what we know, and we're going back to this 1 mole of gas at STP. So the 1 mole of gas at STP gives us our initial conditions. So that means we know that our pressure 1, is going to be 101 times 10 to the 3rd pascals, right? Because we know that is standard temperature and pressure, and we know our temperature is equal to 273 Kelvin because STP, so that's temperature 1. And then because we did example 1, we know that our volume is 0.0224 meters cubed. If you don't remember that from when we did example 1, go back and look at example 1. And this is all for n equals 1 mole, which we don't really need to worry about, but it's still important for knowing the PV equals nRT. So remember, as we did in the last problem, if you have PV equals nRT, you can always make one side a constant and then use ratios to figure out the variables that you're missing, okay? And because you're using ratios to figure out the variables that you're missing, when we're going from 1 to 2, which is this purple process, that means we have an isochoric, meaning V1 is equal to V2. So that means we know, based on what it says here, we're doubling the pressure, so P2 is equal to 202 times 10 to the 3rd pascals, okay? Our temperature is definitely going to be changing, so we have to figure out what that is. But our volume should stay the same. So in order to figure out our temperature, we have to use our ratios. So that means V1 over T1 is equal to V2 over T2. We derived this in the previous problem example. So I think that was problem 2. So if you want to go over that, then you can go back and look at how we did that. It's either in problem 1 or problem 2. I'm not going to go through that derivation again. So that means we want to solve for T2. So T2 is going to be equal to V2 over V1 T1. So we plug all that stuff in. That means we get basically twice our temperature, because remember V2 is twice V1. So we get 2 times, where's T1? Oh, 273 Kelvin, which gives us 546 Kelvin. So we know that now we have 546 Kelvin, okay? So I'm gonna just move this over so we don't use up too much space. So all of this is the transition from P1 to P2. Okay, so we used this T to get T2. All right, so that gives us our values for our pressure and our temperature. So we could actually write these in over here. So volume 1, this is going to be 0.0224, and this is going to be 0.0448, right? Because we're doubling it. And then our first pressure is 101. I'm going to call this kilopascals so we don't have to write the 10 to the third. And then this was 202 times 10 to the third pascals. Okay, so we know all the values on this chart. We're just looking for the temperatures because it's pretty easy to calculate the temperatures and the pressures and the volumes. So then next, as we're going from 2 to 3, remember going from 2 to 3, this is an isothermal process. So T2 is equal to T3. Our isothermal process we're going to represent in blue. Okay. So during the isothermal process, we see that we are changing pressure and we're changing volume, but we can read, since we know things are doubled, right? We can, and halved, we can read things right off of the chart. So from 2 to 3.2 to 3, our P3 is going to be equal to 202 times 10, back, 101 times 10 to the third pascals, because you can just read this off the chart here. And then our temperature 3, well, that has to be the same because this is an isothermal process, so that's still 546 Kelvin. And then our volume 3 is going to be it's doubled, right? So 0.0448 meters cubed. Okay, and you can just read that off the graph. That's something that's told to us in the problem. So now we have everything for P3, and then in this last process, 3 to 4, this is an isobaric, meaning our pressure 3 is equal to pressure 4, which is also pressure 1, because remember 1 and 4 are the same point. And so we go back to all the values from P1, P2, etc. So that gives us back the same values we had at the beginning. So now that we've labeled the graph and we know the temperatures are really the only thing that we didn't have before. So having the temperatures at each point, temperature 1, temperature 2, and temperature 3, now we know all of the pressure, temperature, and volume at each point, 1 through 4. So, and just to, as a reminder, this is equal to P4, T4, and V4 because this is a complete cycle. All right, so just to check, we're looking at this as this graph is a complete cycle. We get back to the same point we started from, and we used PV equals nRT for everything else. You can calculate the volume in this other part by using the same sort of ratio where P1 over T1 is equal to P2 over T2, and then solve for, P2. That doesn't end up being necessary because we are doing these simple doubling and halving processes, but you could do that if you wanted to calculate the temperature going back. It's not really necessary. Okay.